Hi, this is Professor Ross at Colorado State University, and today we're going to be going over the Introduction to our Aqueous Acid-Base Chemistry module, and we're going to talk about why acid-base chemistry is so important for understanding water quality and aqueous chemistry more generally. So by the conclusion of this module, you and other students will be able to describe acid-base reactions, understand pH, pOH, and pKa, and calculate reactions using these concepts. Understand buffers and how they link to environmental chemistry and really control environmental chemistry, and understand environmental sources of acidity in buffers. So I think of acid-base chemistry as one of the sort of key concepts when we're thinking about controls on what's in our rivers and waters. And if you're thinking about this from sort of a more water quality perspective, we can think about what are the pollutants in the environment and what is the main cause of pollution. So if we're looking at this figure from the USGS, we might see something like a septic tank over here, and that maybe you might think of as a nutrient problem, but when there's septic tanks that sort of are releasing into rivers, that also can be an acid-base problem. We have other examples too, like wastewater treatment plants. Wastewater treatment plants can really change the pH of water, and so they're heavily regulated in order to avoid that. And so we can think of sort of each one of these impacts, with fertilizers being another one. You might initially think that that's a nutrient problem, but it also can be a problem about acid-base chemistry. So when we're thinking broadly about water quality, many of the sort of reactions we think about at their core have some acid-base chemistry in them. So this is sort of just a figure that we're going to come back to several times in this class, thinking about how each of these land uses and different point and non-point source pollutions impact freshwaters, and we'll be applying different aqueous chemistry concepts in each of these places. So today we're focusing on acid-base chemistry. So by the end of this specific video, your students will be able to explain why acid-base reactions govern much of aqueous chemistry and water quality, and understand exactly how the Flint water system became a hazard, with focusing on sort of the acid-base impacts. So what is an acid-base reaction? Well, this is actually quite a hard question. You'll see in some of the future videos, people have been spending a lot of time trying to think of the best way to define an acid-base reaction. The most ancestral of these definitions was from Arrhenius in the late 1800s. And that definition is basically anytime a substance adds a hydrogen ion or a hydroxide ion to a solution. So if it adds a hydrogen ion, that means it's an acid. And if it adds hydroxide ions to solution, that means it's a base. And so if you would just look at some common acid-base reactions that might be familiar from your high school or college chemistry classes, when you add something like hydrochloric acid, HCl here, to solution, you will get out hydronium ions and chloride. And really H plus hydrogen ions, which is how we will speak often of acidity, is not a real thing. It always makes hydronium ions, these H3O plus, so that's sort of the real reaction in the environment. But this is the sort of net reaction of hydrochloric acid. So hydrochloric acid here is a strong acid. It's donating its proton to water, and that's making this solution more acidic. We can also think about sort of the inverse, a strong base. So sodium hydroxide here. Sodium hydroxide here is reacting with water and producing sodium ions, a hydroxide ion, and then leftover water. And in this reaction, we're producing a bunch of hydroxide, so we're making the solution more basic, and we'll sort of go over these concepts more, but this is just a general definition. And so in this one, the sodium hydroxide really donates the hydroxide ion, and that makes it a base according to Arrhenius. But what do we do with this Arrhenius definition with something like hydrochloric acid plus ammonia making ammonium and a chloride ion? There's no donation or movement of a hydroxide ion or a hydrogen ion, so it doesn't sort of fit this definition, because in this equation there's no hydronium ion created or a hydroxide ion created. And so Bronsted and Lowry knew about this problem, and they came up with a much simpler definition that we'll be using in this class, which is that an acid-base reaction involves either when an acid donates a proton or a base receives a proton. And so that's a more general definition. And if we look back at our equation here, with hydrochloric acid and ammonia and then ammonium, basically the hydrogen from the hydrochloric acid was donated to the ammonia, and that sort of accepted that proton. So now we can sort of say this is the acid, the hydrochloric acid is the acid, the ammonia is the base, and the ammonium here is the conjugate acid, and then chloride is the conjugate base. So we will sort of use this concept to think about acid-base reactions, and really fundamentally acid-base reactions are about the exchange of hydrogen and hydroxide. And we're not going to use the broadest possible definition of acids in this class because it's a little too intense for what we're going to cover. But there's another model called the Lewis acid and base model, where an acid accepts an electron pair and a base donates an electron pair. And that came later to incorporate a broader suite of reactions. But really for environmental chemistry, aqueous chemistry, water quality studies, the Arrhenius and the Bronsted-Lowry model cover what we need. So a key concept that you should come away with in this module is that the pH, or the amount of hydrogen in solution, so the net sort of reaction of acid and bases, is a master variable that controls many aspects of water quality, including the complexation of ions, the dissolution and transport of metals, the control on life's critical functions, and a whole suite of other things like acid-base chemistry and sort of weathering rates and all kinds of things we're going to cover in this class. We're always going to be coming back to this idea of pH as a master variable, or acid-base reactions as a master variable. And many of you probably sort of, when you think about acid-base reactions, one of the things that I think comes up in a class like in a geochemistry department or in an environmental science department is acid mine drainage. So this is just an image of an acid mine spill in Ohio, and just showing this really red water, and that's because the pH was so low that it dissolved out a bunch of metal, including iron, which has this really sort of red-orange color. And so this is sort of just like an example of the acid-base control on water quality more generally. So I want to zoom back to Richard's example that he gave on the Flint water crisis, and he was really focusing on equilibrium chemistry and acid-base reactions. We can think of them as equilibrium reactions. And I just want to zoom in a little bit more on what happened in Flint and how lead got into the water supply for thousands of people. So as Richard explained in his video, basically lead pipes are a known problem in terms of the potential for lead to leach into solution, but there's been historic treatment effects that build this sort of mineral casing around the pipe to prevent lead from leaching directly into water. And historically in Flint, Michigan, their water supply came from treated water from Detroit, and this casing that protected the water from leaching lead was at equilibrium with the water and the pipe. And so basically this mineral protection layer sort of was constant, and people could drink water and it didn't have much lead despite having lead pipes. And Richard sort of just said minerals and equilibrium to focus, because that's what he was focused on. But for this module, we're going to focus on acid-base reactions. And so one of the minerals that made this casing that prevented lead from leaching into solution was lead carbonate, plus a bunch of other stuff. And so when the water supply switched from the Detroit treated water, which had a pH of about 10, to the Flint River water, which had a pH of 7 or 8, a suite of reactions happened that sort of favored dissolving this protective mineral layer. And that included taking this lead carbonate, which is sort of always at equilibrium between being lead and carbonate ions. And so some of it's always leaching in and out, but at relatively high pH, there's relatively little lead in solution and there's more carbonate. So if you add an acidity, so you change the acidity of the water by switching from the low acidity water of the Detroit water supply to the Flint River, then you sort of change the equilibrium between this reaction, and you consume a bunch of this carbonate. And what that does, and we'll learn about this a little bit later, why this exactly happens, but when there's less carbonate, that means that there's more lead for this equilibrium reaction up here. And so because we change the pH, then you'd sort of dissolve this mineral shell, and that lead carbonate becomes free lead in the water. And so this is just an example of the sort of like interactions at equilibrium that we covered in thermodynamics that we covered in the first module, interact with things like acid-base chemistry to sort of control water quality and the character of water in the surface of the planet. So thanks. There's links to some of the resources here, and I will see you next time.